We have started the Meeting Einstein Lectures, and this is one of these, where we introduce scientists of this caliber. And today we have John Hartwig, who is a guest of the cluster, the catalysis cluster. Thank you, John, for being here.
So as you learned from the introduction, and maybe some of you in the room know this, I'm a synthetic chemist. I became a chemist because I like to make things. As a child, I always liked to make things more than I like to read, actually. So I was always using my hands to do things. And then when it came time in college to choose a major, I really enjoyed my time working in the laboratory and to sort of translate those skills and aptitudes and interests as a child of making things to doing that in a more academic setting is why I became a chemist. And these days, although I don't work in the laboratory anymore, I work with a group of people who do work in the laboratory, and it's a thrill to have them come to me and say, we were able to do this, I made this. And one of the thrills of being a synthetic chemist is to be the first person ever to make a particular substance, right? Or to invent a reaction that allows people to make a substance and have that be a new chemical reaction. And so our research, the sort of pleasure and enjoyment we get out of that research is to make new molecules and to figure out new ways to make those molecules. And these days, the importance of that in general is to make molecules that have important functions, whether they're the coating on an iPhone or a new pharmaceutical or a new material that's made from renewable resources, or whether it's a new way to make energy, as Matthias mentioned, from sunlight, water, carbon dioxide, those sorts of things. And certainly those are the modern problems that we have and that I'll talk about in my lecture today, and catalysis is certainly one of, if not the major entry into solutions to those problems. And so it's, I guess, fortunate that the field that I chose because I like to make things is now a field that allows us to have a great impact on how we go forward in using resources on our planet. So as I said, I'm a synthetic chemist, and so what does synthetic chemists do that people in the room would be interested in? So I know there's a fraction of people who are chemists, a fraction of people who are scientists who aren't chemists. Maybe there's people here who aren't scientists at all, I'm not sure. And so I'll try to, in today's lecture, give the chemists maybe a different perspective on the things that they think about every day, and the scientists some perspective on what synthetic chemists do. So chemical synthesis makes everything around us, right? The carpet, the coatings, and so a classic example of what synthetic chemists do is to make things that are important to human health, make pharmaceuticals, make new materials that can be something like an artificial hip or sutures that would dissolve in the body. They feed us, making the fertilizers, and for better or worse, the pesticides and herbicides that lead to high yields. They get us around by transportation, providing the fuel that makes the car run, but also the large number of plastic parts that are in a car that make it light enough and improve gas mileage, to things that make us safe or make us happy, I guess, feel like we're faster runners than we actually are. The amazing electronic advances, the new modern flat screen displays, or as I mentioned, the coatings on the iPhone and the parts that make it so that if you drop it, it doesn't always break, at least, or new energy sources, and even things that are made of a natural substance like wood, right? So I happen to be a particular fan of arts and crafts furniture, and the coloring comes from ammonia, and then the finish on it, of course, are things that are made by synthetic chemists. Okay, so if we make all of these things, and have been making those sorts of things for many years, how has synthetic chemistry changed over the last decade or two? So I think of the way synthetic chemistry has changed as being really a revolution over the course of my career. It's been slow, and it's not something that's in the front page of all the newspapers. But nevertheless, synthetic chemistry as it's practiced today is really completely different than it was 2 decades ago when I began my career. And so how is that? Well, it's because people have developed catalysts. Catalysts to do the kind of synthetic chemistry that if one were to learn about it in an introductory organic chemistry class, you'd learn classic reactions that don't involve catalysts, that involve things that are, reducing agents, that burn in air, and that are using a lot of the, resources to generate those materials. And instead, now we use catalysts in very under safer conditions. Okay, but catalysts aren't new. Right? So you in your body is made through chemical synthesis. It's just that chemical synthesis is done with catalysts called enzymes that are proteins. Right? So we're all just a bag of chemicals and that are being made constantly and regenerated by these enzymes. Right? I'll get back to that in a minute. And so, just a representation of what these catalysts look like is that they have a large amount of organic material, carbon, hydrogen, nitrogen, and oxygen containing amino acids that are these blue and yellow ribbons around here. And in the center of this enzyme is a metal. And that metal is iron, and that iron will oxidize hydrophobic or greasy compounds that are in your body and make them more water soluble. And that enzyme's in your kidney, and that allows you to excrete the toxic substances that are in your body. Right? So that's what your liver does. It's a P450 enzyme. And on all of this very large catalyst is this very small iron center in the middle that does the reaction. So as Matthias mentioned, catalysis is also done in the chemical industry on massive scale. And so here's a picture of, I think, a petroleum refining plant, the largest scale chemical synthesis that's done. So there's some distillation towers, but in these pipes are catalysts that are solids that redistribute carbon-hydrogen bonds and carbon-carbon bonds and lead to some of the feedstocks that we use. And so this is done on absolutely massive scale, as I'll talk about in a bit. Okay, and so these days, when we think about organic synthesis toward small molecules that have a particular function, like the one down here that I'll touch on later in the talk, right? A lot of what we've been focused on as a community and in my own group is to take inspiration from enzymes and from the commodity chemical synthesis to make molecules that have a specific function, say for a medicinal chemistry purpose, and to do that with catalysis, do it in a very controlled and precise way. And so if we're going to do that, and if we're going to continue to do that in an improved way, we really need to think about how we can convert catalyst discovery from an empirical activity, something which is very Edisonian and has made remarkable advances over the years by many serendipitous discoveries, and change that into something that's much more of a design process where we can plan to the kind of catalyst we want, and I'll touch on that in a little bit. All right, so the kinds of themes that I want to touch on today are the following, right? So I want to talk about catalysts, what they are, and a little bit more precisely what they do. But I want to talk about what people make, and I want to spend a little bit of time talking about the scale of chemical synthesis, the massive scales that fill up tank cars, and what some of the potential alternatives are for feedstocks to do this kind of synthesis, for example, using sugar cane, and whether that's realistic or not. I want to then talk about an alternative way to do chemical synthesis that relies on reactions that occur at carbon-hydrogen bonds, and then hopefully I have time to talk about some new ways that we think about discovering catalysts. All right, so three main topics that I'd like to touch on today. All right, so first, what is a catalyst? Matthias said in words. I'll give you a few pictures. So we all use the word catalyst or catalysis in an everyday vernacular, whether it's a perfume, or I guess this is actually a men's cologne, or whether it's a venture capital firm, or whether it's a social nonprofit organization. Okay, so if you look at these, it's not. These sites, it's not clear they really understand what a catalyst is. But what a catalyst is, in chemistry at least, is that it's a reaction component that makes a reaction faster but doesn't change during that reaction. Okay, so it's got to be the same at the beginning and the end of the reaction. And it can be big, as I showed you, an enzyme. It could be just a proton, right? Hydrogen atom minus its electron. It can be soluble, meaning that it's in the same, and homogeneous, it's in the same phase as the reactant, or it could be a solid that reacts on a gas and is called heterogeneous. Right? And so it makes reactions more efficient, lower temperatures, for example, faster rates. It can make them more selective. So if you make 2 or 3 different products without a catalyst, with a catalyst, you can selectively form one product over the others. And it can take reactions that would take a sort of geologic time scale to occur and make them happen in an afternoon in a laboratory at room temperature and atmospheric pressure. All right, so where do we get these catalysts from? Well, first, what's organic chemistry? Well, organic chemistry is this part of the periodic table up here on the top right. So it's carbon, nitrogen, oxygen, sometimes phosphorus, but mostly CNO, phosphorus, and a little bit of sulfur, right? Sometimes halogens. All right, so the catalysts can be made of these elements as well, and certainly there's a growing area of organocatalysis. But a majority of catalysts are from this part of the periodic table, which is the expensive part of the periodic table, right? So that's the rhodium, platinum, palladium, iridium metals, and those are called noble metals in some cases, and they are the bulk of the catalysts that are used in a catalytic converter of a car or petroleum refining and so forth. There are a few that are over here. Titanium and zirconium are catalysts for polymerization that I'll talk about as well. So one of the challenges that I'll touch on at the end is whether we can make catalysts out of the rest of these transition metals that are the chromium, manganese, iron, cobalt, nickel metals that are the inexpensive metals and are more abundant and are perhaps more easily mined than the platinum, rhodium, and iridium based catalysts. All right, so how does a catalyst work? If it makes a reaction faster, how does it do that? Okay, so here's a kind of picture that chemists use to describe what happens energetically in a reaction. So along the y-axis here is energy. So we start at some energy of the reactants, and as the reaction goes on, it has to go over a barrier, an energetic barrier. And then it gets down to the products, and the products have to be more stable if they're going to get formed. So this would be exothermic or exergic reaction. Okay, so it's a little bit like a hiking map or depiction of what you're facing when you start a hike. Okay, so what a catalyst does then is to create a new pathway that's lower energy, right? And so that pathway would have more hills and valleys than the uncatalyzed pathway, but the peaks of these hills are lower than that. So there's lower energy to get over here and then over there and over there and over there. And so part of the creativity of doing catalysis and inventing catalytic reactions is deciding what all these hills and valleys should be. And part of the puzzles of understanding existing catalytic reactions are what each of these steps are and how we can make them faster or more selective. All right, so another view of the way a catalyst works is to draw this in a cycle, right? So we'd start off with a catalyst, and we're going to draw this in a circle because remember, a catalyst can't change, so you have to get back to where you started from. So a catalyst would start off, and let's say we've got a molecule with 2 halves, we'll just call it A and B. So the catalyst would come in and break that molecule in half, okay, and to attach those to the 2 ends of the catalyst. So now if I'm the catalyst, I got A here and I've got B there. And so then we need to modify those to make the chemical reaction occur. So we could take a third portion, let's call it C, and insert that. And so now we've got A here, and now we've got the catalyst now connected to part C. And then in the end, the catalyst takes those 2 parts and puts them back together, creates a new molecule, ACB now here, but it comes back to where we started from. Okay. And so, if you will, this is in some ways a chemical assembly line. Right? So the molecules come in, parts get assembled on them, and then it gets passed off. Another molecule comes in, you add some parts on the side, and it gets passed off. Right? So another way to think of it is that it's a chemical matchmaker. It takes 2 molecules that don't want to be together, right, or don't know that they want to be together, let's say, right, and you make a bond between the 2 of them. And the analogy is such that there's actually a website called chemistry.com, which has nothing to do with chemistry. It's a dating website, I learned. So I learned a little bit by putting together this talk. Right? Back to that point later in the seminar, actually. Okay, so how do we decide whether a catalyst is a good catalyst or not? So there's some metrics we put to this, and so one of those is called turnover numbers. So that's the molecules or moles of product for every molecule of catalyst, right? And so hopefully that number would be large. That would mean that the assembly line works a very long, many times before the catalyst decomposes to something that's inactive. And then the second metric, which maybe is more important for practical processing for an engineer, is turnover frequency. So that's the turnover numbers per unit time, or how fast the reaction goes, or how fast that assembly line is working. And so just to put this in a little perspective, right, on scale. So here's a bag of rice that's 9 kilos, 20 pounds of rice. And so if you make that amount of material from 2 aspirin tablets worth of catalyst, that's about 10,000 turnovers at the normal weights of catalysts and molecules. And so if you're at 10,000 turnovers, you're not going to make things on the billion pound per year scale, but you're certainly in the range of things that are cost effective to do to make fine chemicals, whether they're agrochemicals or of high value polymers or a pharmaceutical. Right? And so this has sort of been our target, is to get to those sort of turnover numbers. All right, so if you add up all of the catalysis related to those pictures that I showed you of the refineries and the iPhone parts and the TVs and the pharmaceuticals, and you add that all up, at least in the US, it's about 10% of our gross national product. Okay. So trillions of dollars annually, and that's true for, I think, essentially any industrialized nation in the world. And so how can it add up to that much money? Well, it's because you got petroleum processing on large scale, catalytic converters in your cars, the small feedstock chemicals I'll talk about in a few minutes. You've got the polymers that Matthias mentioned. You've got crop protection, fragrances, and pharmaceuticals. And so if you think about the scale, right, we're increasing as we go up here from kilograms to billions of pounds. And the value increases as you go down. So is, a petroleum company worth more than a pharmaceutical company, right? They both make chemicals in the end. Okay, well, the companies are worth about the same because the pharmaceuticals cost more than the gasoline does. And so you add it all up and it adds to, it's roughly the same value because they balance out. All right, so if there's any chemists, any people here who aren't chemists, I'm going to show chemical structures, so I thought I would just give a little refresher on what molecules are. Right? So atoms are electrons around a nucleus. The electrons are negatively charged, the nucleus is positively charged. I pulled this off the website. It's not a very accurate picture of an atom, but there was the nucleus and the blue things are the electrons going around the outside. All right, so a chemical bond is formed by sharing electrons between 2 atoms. It's, if you will, the glue that holds the nuclei together. And so we draw structures such that a bond is a line between the letters representing the atoms. So that would be methane that Matthias mentioned in the beginning is a real challenge to do reactions on methane. So it has 4 carbon-hydrogen bonds. And at least in one picture I pulled off the web, here's a little depiction of the electrons around the carbon and the 4 hydrogens. And so the molecule is held together by having this cloud of electrons around the bond. All right, so that's a carbon-hydrogen bond is the way we draw that. Another way we draw chains of molecules with carbon-carbon bonds is just like this. And so this depicts a carbon atom here, a carbon atom here, a carbon atom there, and in between those is a carbon-carbon bond. Okay? And we don't draw the hydrogens because that takes too much time if you got to draw them all in. Okay, so then this molecule has just carbon-hydrogen bonds. That has just CH bonds. So there's no what we call functional groups on that molecule. There's no place where typical organic reactions take place. But if we take acetic acid down here, now this has a carbon-oxygen double bond depicted with 2 lines. Right? And so that's a functional group. So reactions that would occur at that carbon atom or at that OH bond here would be a second type of functional group. That's acetic acid, which is in vinegar. Right? And then methanol, or wood alcohol, is this one, and so that has a carbon-oxygen single bond in it. And this is a position where a reaction might occur around that part of the molecule. Right? And so we also then depict the portion of a molecule that doesn't usually undergo a reaction just with the letter R, R standing for radical. And so that would be all this stuff out here with carbon-hydrogen bonds that doesn't usually do any reactions. And so we would write this alcohol as ROH because this is the part where of the molecule where the reaction usually occurs. Okay? And so I'll get back later in the lecture to this business of this notion about where a reaction occurs and where a reaction doesn't occur in functional groups as we go on. All right, so I want to talk a little bit about the scale of chemical synthesis and what some of the challenges are in catalysis accomplishments, I guess, and what some of the challenges are going forward. So here's 2 molecules, ammonia and acetic acid that I just showed you. Right, so the scale of ammonia synthesis is 200 billion pounds per year. Sorry about my pounds and all my numbers, right? But just divide by 2, close enough for kilos, right? So 200 billion pounds per year, and that was 10 years ago, so it's probably 250 at this point. All right, acetic acid's a smaller scale, but still 5 billion pounds per year. So what's 5 billion pounds? How much material is that if it's a liquid? Well, it's 1,000, by my estimate, 1,000 Olympic-sized swimming pools full of acetic acid we produce as human race per year. So I don't know if you think that's a lot or not a lot. It seems like a lot to me. I'm not sure I've even seen 1,000 Olympics. I can imagine the size of that. Okay, so this is produced by a heterogeneous catalyst, an iron catalyst on alumina, and it's nitrogen plus hydrogen to make ammonia, the Haber-Bosch process. Acetic acid, classically, has been made with a rhodium catalyst with just carbon monoxide attached to the rhodium, and it's methanol plus carbon monoxide with a promoter to make acetic acid. I'll get back to that in well, actually, I guess what did I just say here? So this process, invented something like 60 years ago at Monsanto, has been changed. Now BP bought the Monsanto process, and they've changed this so it's actually catalyzed by iridium. So although a process might be 60 years old and you think you could never improve on how well refined it is, you can change that from rhodium to iridium if you add a promoter. The reaction's faster. It uses lower pressures of CO. It actually uses less water. You get less water in the product. And that's a big deal because separating water from acetic acid actually costs a lot of energy because you got to distill to separate the two. Right? And so this is a much more efficient process and is now the way this is done. All right, so what's the importance of the Haber-Bosch process, right? It was invented here in Germany before World War I. And so that was around 10, somewhere in there. And so that's allowed for this huge growth in the human population. So for better or worse, right, the human population has grown to the 7 or so billion people that it is because of the Haber-Bosch process. So why is that? Well, ammonia is fertilizer. You take ammonia and you add an acid to it, phosphoric acid or nitric acid, and you make nitrogen fertilizers. Right? And it turns out that of the nitrogen atoms in your body, half of them came from the Haber-Bosch process. Right? Whether you eat organic or not. Right? So you know, the ammonia fertilizer goes on the ground, the plants take up that nitrogen, you eat the plants if you're a vegetarian, or some other animal eats those plants, another animal eats that, and then you eat that animal. And those nitrogen atoms that are in your body and all those amino acids and the proteins that are in the enzyme, the P450 in your liver, those came from the Haber-Bosch process, chemical synthesis. Right? And the hydrogen that's used to make the ammonia comes from petroleum. Right? And so a massive amount of hydrogen is used to put onto nitrogen to make ammonia, to make fertilizer. Okay. So I guess what, you said 3% of the power of electricity or total power in the world is used to run the Haber-Bosch process and to make that hydrogen. All right, so what about the acetic acid? What do we do with all that acetic acid? Right? Well, I don't know if Germans eat a lot of pickles, right? Make pickles that's in vinegar, right? Or a French vinaigrette or something. But there's no way you're going to use 1,000 Olympic-sized swimming pools full of vinegar to make pickles. So where does it go? Right? And so you're not supposed to be able to read this, but here's acetic acid. And just appreciate that this is this tree, right? This goes in to make one thing that's used to make several other things. And along this axis here are things like herbicides, detergents, pharmaceuticals, plastics. Actually, you know, glue is a polymer that's made a derivative of acetic acid. And so, you know, you get a base chemical like this goes into the chemical industry and it makes all of these things. And so that's why 5 billion pounds of acetic acid are made per year through a catalytic reaction. All right, so let me talk about a couple other catalytic reactions that are used now to make materials, polymers, actually the carpet that I'm walking on. Okay, so adiponitrile is what this molecule is called. Old numbers, but on the order of similar now, at least 2 billion pounds per year of that is made. Okay, why do we make that? We convert that to hexamethylene diamine, this diamine, which you then combine with adipic acid, this diacid, and that makes nylon 6,6, right? So that's the typical nylon. So we make a lot of nylon, and that's why people make billions of pounds per year of adiponitrile, and that's done through a catalytic process, a classic catalytic process of a nickel catalyst with a phosphide attached to it, and you add hydrogen cyanide across butadiene, and you make that molecule. And it's actually amazing if you get into the guts of how that works, that it can occur that selectively to make that product. All right, so there's a company called Renovia that's actually just started 1.5 years ago, which appears to be making great progress toward an alternative way to get to adipic acid, and you actually can convert adipic acid to adiponitrile from glucose. Right? So here's glucose, it's a sugar, right? And so if you draw that in an open form, it's this. So you can oxidize the ends to make glutaric acid, and then do a hydrogenalysis, a reduction, to remove the hydroxyl groups, and you get to here. Okay, so that's a process that they're developing, this couple of people who are classmates of mine from Berkeley are developing, but you got to wonder how well, you know, let's say just the challenge that there is, because you got to be able to do this on a scale of 2 billion pounds per year to partner with this nitrile to get to here. So can you really do that reaction on 2 billion pounds per year and sell it for $1.25 a pound, right? Because if you got to sell it for $10 a pound, someone's going to buy it for $1.25 a pound through the classic other routes that are used to do this. So that's the challenge of being able to use one challenge, being able to do renewable resources to compete with this sort of absolutely massive scale of what's already being done at a very low cost. Now the same is true for polymers. So polyethylene is the polymer of ethylene. It's not always perfectly linear, but we make 120 billion pounds per year of polyethylene. It's more than the weight of the people on the Earth, I think. So, or about the same, right? 7 billion people, what's the average weight? Right? It's about that much. Okay, polypropylene is on that sort of a scale. All right, so this was also invented in Germany by Karl Ziegler, 52, Nobel Prize in 1963. Okay, so again, it's another 60 or 70-year-old reaction, but it's not, well, a lot of it is made through some of Ziegler's early catalysts, but now you can make polypropylene with very controlled way, and the key here is that all of these CH3 groups or methyl groups have to be on the same side of the polymer for it to be a useful material. Okay? And that can be done with catalysts with architectures like that, right? These metallocenes. And you can actually take ethylene and propylene and polymerize them together to make a material that's linear low-density polyethylene, and that's done with a catalyst that looks like this. So if you take a plastic object and you tip it over, take a yogurt container, tip it over, it says PP on the back, and that's polypropylene. Right? And you flip some other ones over and they say PE on the back, and that's polyethylene, and some say HDPE, high density polyethylene, or LDPE for low density polyethylene. And so those are made through these catalysts on these sort of scale. All right, so can we make biopolyethylene, for example? Right, so you can take ethanol and make ethylene, that's pretty easy. And then you can take the ethylene and make polyethylene. So can we get enough ethanol to do this? Does that make any sense? All right, so by at least one website, they say that 40 billion pounds of ethanol are produced per year in Brazil using about 2% of the arable land. So it's claimed that that's, you know, not really leading to deforestation. That's not really cutting into the food supply. I'm not knowledgeable enough about the details to argue with that. Maybe some people here know, but that's some of the statistics of how much is made. All right, so, but that's 40 billion pounds, but we make 120 billion pounds per year and you lose some mass. So you have to do this on a much larger scale than what's done here. And then most of the ethanol that's created by fermentation of sugarcane in Brazil is not used to make polyethylene, it's used to make fuels, ethanol fuels. Right? So liquid fuel is 8 trillion pounds per year. Okay, and so if you're going to make the liquid fuel from ethanol, you need 4 Brazils completely, rainforest and everything wiped out, growing sugarcane to get the ethanol to provide the fuel for the world, right? The fuel and then the polyethylene. So maybe you could create enough ethanol to make the polyethylene, but we can't make fuel that way, I don't think, right? So maybe a farmer in Brazil can make a good living growing sugarcane and making some ethanol because it can be sold at a competitive price. And, you know, that's great for that person, but in terms of a way out of the fuel issue, the liquid fuel issue, you can't solve it, I don't think, through sugarcane. 1/3 of the corn in the US is turned into ethanol, right? But that's a small amount of the fuel that we use. So if you're going to turn all of the fuel from ethanol, we don't have any more corn. maybe it's okay. All right, so the other thing I just saw the other week, 2 weeks ago in the New Yorker. New Yorker's a magazine that's a well-respected, highbrow magazine in the United States. And so there was this article on using fungus to make a foam material that would replace polystyrene. So I actually think the article is pretty irresponsible, right? People thought, a number of people thought, oh, that looks really cool, and then actually commented to me. We make 38 billion pounds of polystyrene per year, and it's 90% air, styrofoam, right? So are you really going to make 38 billion pounds of fungus that you can use as packing material? That seems completely ridiculous to me. So maybe at the cocktail session or something, you can say that it's not, and you can make that much fungus, but I don't think so. right? And so again, it's this issue of scale, right? Maybe one person can make enough money to, some special packing that makes a few people feel good, but you're not going to affect the amount of polystyrene out there. All right, so that's the end of my lesson about scale. And so we in my group are working on ways to create fuels from, let's say, invent the reactions that are used to make fuels that are maybe of the future. And one example is to be able to use lignin. So plants have cellulose and lignin. Cellulose is what you can ferment to make alcohol, and then there's the lignin part, which makes the plant stand up, right? So makes the plant stiff. And it's a material that has all these aromatic groups, these 6-membered rings, and oxygens in it. And so if you want to take lignin, and well, right now lignin's burned, and if you want to take lignin and turn it into something that could be a fuel or a feedstock chemical, you got to take all the oxygens off of that ring. So you need a reaction that will remove those. And so Alexei Sergeyev in my group discovered this reaction of catalyzed by nickel with hydrogen that will cleave the carbon-oxygen bond here to make benzene and phenol in very good yields. Right? It's published in Science. Very selective reaction, the first reaction that could cleave that CO bond without reducing the benzene. Okay, so is this a major, big step forward? I don't know. We'll see if anybody refers back to this 10 years, 15 years from now, if anybody does something with lignin. But we need to make 8 trillion pounds of fuel was the number, right? And we've got 5 turnovers. We've got 20% nickel in here. We're a long way from doing anything, and that's right on a pure material, not on lignin itself. So that's one of the challenges, right? You've got a reaction like this on a pure material that's a brand new reaction, and it's got to go all the way to being able to use a mixture and a heterogeneous mixture of the biofeedstock at the kinds of costs and scales to be able to do things on a billion to trillion pound per year scale. That's a really tall order. So we'll see if we make progress toward that. We're continuing to work on this, and I'm pretty optimistic that we'll come up with something that becomes practical, or the community will. All right, but let's talk about synthesis for function and a new way to do synthesis and discover catalytic reactions. All right, so if we think about synthesis for function, the classic function is medicinal activity, right? So many chemists are oriented toward making compounds that improve human health. So here's a compound, losartan. That's a $1 billion drug. It's antihypertensive for high blood pressure. Okay, so if you think about how you would make that molecule using classical organic chemistry, the kinds of chemistry you teach to introductory undergraduate students, right? How would you ever get that group attached to that end of these 2 rings and something attached to that end? There's just no chemistry to do that. You can't make that molecule through classic organic chemistry. All right? And so that's where catalysis comes into play to be able to make molecules that have this type of activity. So there's a reaction called cross-coupling, where one can take this ring with a zinc attached to it and attach that to this ring with a bromine attached to it through a reaction called cross-coupling catalyzed by nickel. So now you've got this molecule with this group attached here and that methyl group up there. And so then through some pretty standard organic chemistry, you can brominate that, and you can make this tetrazole, and you can put that group on there, and you get these family of drugs. There are many of these antihypertensive drugs in the sartan family. Right? And so Negishi discovered this particular version of the reaction with the zinc reagent, and then Suzuki discovered that with a boron reagent, and those are named cross-coupling reactions, and the 2010 Nobel Prize in Chemistry was for cross-coupling, because you can make these sorts of molecules that lower blood pressure. And if you think about what that molecule does, right? You got high blood pressure, maybe you have high cholesterol, I've got high cholesterol, right? And you take a little pill, it's this organic chemical that's been pressed together with maybe some binders or something, and you eat that, and your blood pressure goes down, your cholesterol goes down, right? It's an amazing thing that you can just take this little molecule and have that happen to this complex body that you have, right? And then get passed out and have it out of your bloodstream at the right amount of time, right? And so synthetic chemists have been able to figure out how to make molecules that have that kind of function. All right, so the second thing I want to talk about for molecules with that sort of function is what we call chirality, or the handedness of molecules. Of course, your left hand and your right hand are mirror images of each other, all right? Just like amino acids, the left hand and the right hand of amino acids are mirror images of each other. So if you look in the mirror, right, you might think that there's actually a mirror plane down your body, and the left side and the right side are almost the same in your body, but they're not at all, right? So your liver's here and your heart's over here, right, the left and the right side. But even more than that, all the molecules in your body are either left-handed or right-handed, almost all the molecules, not the water, I guess, but the proteins, the carbohydrates, the nucleic acids, they're all left-handed or right-handed, but not both. Okay, so if you're going to think about making a drug, you need to make a drug that is either left-handed or right-handed, right? Just like if you shake hands with someone with both two right hands, your hands fit together well, but if someone has the right hand, someone has the left hand, then it doesn't work, right? Your hands don't fit together. And so if you have a protein that you're trying to interact a drug with, right, and the protein's right-handed, then your drug's got to be right-handed so they fit together. Okay, so the other thing is that if you have a molecule that has different sections of it that can be right or left-handed, if one's right and one's left, that's a different molecule than if they're both right, right? So if you had two right hands or two left hands, you couldn't do the same things you can do with one right and one left hand, right? And I guess my analogy, just because I'm now here in Europe, was a soccer team. And so if you have a left-footed and a right-footed forward, then I think you're better off than if you got two right-footed forwards, right? Isn't that right? So you can kick the ball this way and this way, both toward the goal. I played goalie when I was, I didn't play forward, right? Or if you have two, first and third basemen, and first baseman are left-handed, third baseman are right-handed, okay? All right, so let's think about this molecule I showed you before, which has a particular function. It's a drug for treating AIDS. It was actually the first effective treatment, reasonably effective treatment for HIV/AIDS. And although it's been superseded many times over by other compounds, it was the first drug that showed that it was a disease that had some chance of being treatable. It was made by people at Merck Process, and so this portion of the molecule comes from this chemical reaction where hydrogen is added to the front side of the molecule and not to the back side, right? And so if the hydrogen comes in and adds this way, you get, let's say, the left hand, and if it comes in from the back side, you get the right hand. And so a catalyst controls whether the hydrogen comes in from the back or the front and makes the left or right hand. And then that's attached to the rest of this molecule, which each has its handedness. So this molecule has got to be like left, right, right, left, left to function. And if it's, if it's right, 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 left, left, it's no good. Right? And so a synthetic chemist has to make each one of those centers in the precise way with the right-handedness or the right chirality. And so that's important enough that the 2001 Nobel Prize in Chemistry was given for asymmetric hydrogenation, for adding hydrogen to one side or the other side of a double bond. Okay, so let's get back now to the kinds of things that we do in my group and the kinds of synthetic chemistry that we try to tackle. Right? So one of the things we really try to do is to think about how to design catalysts. So the cross-coupling reaction, the hydrogenation reaction, the Ziegler catalysis, a lot of these sorts of reactions, olefin metathesis I haven't talked about, were discovered rather serendipitously. Okay? And then people appreciated what the importance was of those and then developed those reactions. Okay? But so could we turn this process of development of those compounds and the discovery of those compounds, as I said, into more of a design than an Edisonian or empirical process? And so inspired by these advances that I just talked about, the goals of the field, including for my group, are to gain an understanding of how catalysis works that's deep enough that it allows us to select or design and then prepare a structure that will have a desired catalytic activity. So you got to be able to make the catalyst, design the catalyst and make the catalyst, and then have it do what you want it to do. Say, take glucose and turn it into adipic acid with 1 million turnovers, right? Okay, so the way we address that challenge then is by using mechanism to design catalyst. Go in and try to understand how each of these different steps of a catalytic cycle with all of its bumps, how each of those reactions work, and whether it's going to be faster or slower if we put more electron density here or put more electron density there in a molecule or make one group bigger or smaller. And by understanding that, then we can go back and perhaps make a better catalyst. And I'll give you an example of how we've developed that in one case. And then the second thing we're trying to do is to at least think about new ways to discover catalysts, new ways to get leads, these sort of serendipitous observations that Ziegler made in discovering the Ziegler catalyst. Could we do that in a more systematic way? And so that's what I'd like to talk about for the rest of the talk today. Okay, so one project that's been a pretty important project for synthetic chemists had its lead from, or seed from, this result. So I started my career in 1992. In 1993, we started working on the cross-coupling, not to make carbon-carbon bonds, but to make carbon-nitrogen bonds. And the lead was this paper by Kosugi and Migito, where they showed that with a palladium catalyst, you could attach the nitrogen from this tin reagent to the carbon where the bromine was to make a carbon-nitrogen bond in an aromatic amine. So it turns out that about, 80% or 90% of drugs have nitrogen in them, and of those, about half of them, roughly, have nitrogen attached to an aromatic ring. Okay, so this is a new way to make those sorts of molecules and really allows medicinal chemists to make a wide variety of those aromatic amines in a much faster way and to do that in parallel in a high throughput fashion. So there are also the components of conducting polymers. Polyaniline is the conductive polymer. Actually, there's a Nobel Prize given for the discovery of polyaniline many years ago. And then some of the layers of organic light-emitting diodes are aromatic amines, the whole transport layers of those. So they're, from material science to pharmaceuticals to agrochemicals, they're important materials. So nobody had studied that reaction for 10 years. There were no citation, very few citations of that paper besides their own. Okay, so why is that reaction important? Okay, so that gets back to what catalysis can do relative to what you would maybe learn in classical introductory organic chemistry. So in introductory organic chemistry, you learn that you can do an SN2 reaction with amines. They're very good nucleophiles, so they seek the nuclei or electrophilic sites. They'll do a backside attack onto this alkyl iodide and make this ammonium salt, right? The standard organic reaction. But if you try to do that if you try to do that with an iodide attached to this flat ring, to an aromatic ring, then the reaction doesn't occur. You could wait forever, and that reaction doesn't occur. Okay? So we need to add a catalyst. Oops, what have I done? Sorry, I'm pushing the wrong buttons here. Right? Okay. So the classic way to make the molecules then would be this way, I think. I don't actually teach organic chemistry, but this is the way I learned it. You take benzene, you'd nitrate that with nitric acid, fuming nitric acid. You'd reduce that to the aniline. You put a blocking group on that. Then you'd put the R group on, the alkyl group, and then you take the blocking group off. So in, 5 steps, you'd go from benzene to the aromatic amine. Okay? If we had a catalyst, we could shorten that synthetic sequence to do the following, right? We could just put on a chlorine, for example, and then use a catalyst to do that coupling reaction to make the carbon-nitrogen bond. So 2 steps instead of 5. But it's actually even better than that because you can buy a few nitroarenes, right, chopping that first step off, but you can buy, when I looked this up about 10 years ago, you could buy 20,000 aryl chlorides. You could probably buy 30 or 40,000 aryl chlorides now. Right? So in fact, most of what you would do would just be 1 step. You'd buy 20,000 of these, and you can probably buy 5,000 amines, something like that. And so you've got a lot of versatility in what kinds of products you would make if you're going to attach things onto molecules to investigate medicinal chemistry. Okay, so that's one thing, that way catalysis can do that. And so we've developed catalysts, as have others in the field, that operate with this sort of 10,000 turnover numbers to make, that big bag full of chemicals from aspirin-sized tablets worth of catalyst. And the picture of the catalyst that I showed you in the earlier slide here was actually this compound, and that's an intermediate in the catalytic reaction with the particular catalyst that we developed in my lab to do that sort of cross-coupling. Right. So there's Matthias Beller's group here in Germany that's developed some great catalysts for doing that chemistry since we've been working on it, and Steve Buchwald's group and my group began studying this chemistry together. And Steve's group has developed some really amazing catalysts to do this chemistry as well. All right. Right. So the second point I make, though, right, as a segue into the other chemistry I want to talk about, is that these reactions still occur at the so-called functional groups, right? So we've got the CH bonds, the R groups off the side, right? But then we've got the carbon-chlorine bond, we've got this carbonyl group here, which is coming into play, we've got the nitro group here. There's all these functional groups on these molecules is where those reactions occur. So is it possible to come up with a different way to make these molecules that would not use classic sophomore organic chemistry? So it turns out I'm editing or whatever, modifying a book on organic chemistry for sophomores that would include a lot of catalytic chemistry. But still, we're going through these chapters, right? So chapter 7's on the nucleophilic substitution I just talked about, but we've got alkenes, epoxides, arenes, ketones, carboxylic acids, enols, amines. These are all the functional groups, and this chapter has described what the reactions are of those functional groups in organic chemistry. So is it possible, though, to design a new organic chemistry, right, or at least a complementary organic chemistry that would be divorced from the functional groups, where the reactions would occur not at the functional groups, but at the portions of the molecule where those reactions typically don't occur? All right, so that takes us to the chemistry of the carbon-hydrogen bond and trying to do catalysis at these portions of the molecule that the classic organic reactions don't occur at, so we can get to new materials. And so here's a few reactions. I won't go into them in detail. Chemists can see these reactions for themselves. So these would be all great reactions to do, but they're all endothermic. They're all uphill. So instead of the reaction going over the hill and down, it goes over the hill and up. And so you can't accumulate product if it's endothermic. So in addition to the thermodynamic problem, there's a selectivity problem. So oxygen or hydroxyl radicals and chlorine radicals will react it with CH bonds to make things like alcohols and alkyl chlorides. But to the extent that they react, they preferentially react at the internal positions, internal CH bonds, and there's usually many of those. And really what you'd like to do is do the reaction out here at the strongest and least reactive CH bond. And even if you do the reactions, now you've got these functional groups in here, and so that's now where the reactions, further reactions occur, and so the products are more reactive than the starting materials. And so if you get to here, then it just goes on, and that's why we burn hydrocarbons, because it just goes all the way to CO2 and water, and if you're doing chlorination, you get polyhalogenated products. So can we use a catalyst to change the selectivity of these reactions, kinds of reactions? And then if you have one of these rings that I was just showing you before, you've got this position, and that position on the ring, and can a catalyst control where the reaction is going to occur on that ring, and change that selectivity from what you learned in sophomore organic or introductory organic chemistry if you took that course. So that's the challenge that we've been trying to address while we've been working on that other CN coupling chemistry. Okay? And so if we could do that, then we could think about changing or complementing the way catalysis is done on an aromatic ring. So I showed you the Negishi coupling with the zinc reagents to make the biaryl bonds here, and there's other reactions to make carbon-carbon bonds, and then there's reactions to make carbon-nitrogen bonds I showed you that happen at that functional group here. But could we do the reactions at the CH bonds to make this set of products, which is a lot like the set of products here, but we've cleaved a CH bond and we've left the X group behind. So then you can come in and do the other type of catalysis, the cross-coupling at those positions, and build up complex structures that might be important in the agrochemical or pharmaceutical arena. And so that's what we have been doing, although I can't say that we aim to do that from the start. At the start, when I first met Matthias working on main group chemistry with main group elements bound to metals, we were working on compounds with metal-boron bonds from the very fundamental standpoint that there's an empty orbital at boron, right? And that would be a Lewis acid at this portion of the molecule, and usually it's the metal that's the Lewis acidic site on the molecule. And this group here, the electrons that are in that bond are going to be pushed way over toward the metal because the boron doesn't want to have those electrons. So this is a very strong electron donor in this direction while being a Lewis acid in that direction, and that would be an unusual kind of group attached to the metal. And so we just wanted to see whether that sort of distribution of electrons would give rise to new reactivity. And indeed, it's those properties that give rise to the ability to cleave and functionalize CH bonds selectively over reaction at the functional groups that are the classic points of reaction of organic chemistry. All right, so the molecules that we've started looking at, so this is going to give you a quick tour through almost 20 years of metal-boron chemistry and CH activation. So our lead was making these compounds with an iron-boron bond. And we photolized these. Actually, I was trying to photolize to cleave the iron-boron bond, but actually that bond was cleaved instead. And what we got out was a compound with a carbon-boron bond where this boron is now attached to that aromatic ring. Right, so a serendipitous observation, although I was very interested in CH bond functionalization from the beginning, and so our eyes were open for that sort of reaction. Okay, so this is not a catalytic reaction. This is changed in the reaction. It's not a catalyst, it's a reagent, but it could be imagined to be a catalytic reaction if we could take this and somehow convert it back to the start to close that loop that I showed you earlier. So we also showed then later that this compound with tungsten would cleave a CH bond at the end of an alkane to make this carbon-boron bond here. And so here's a reaction that was unlike the reaction with oxygen or hydroxyl radical or chlorine, because now the group is attached to the end of the chain, cleaves the strongest CH bond. It's the only reagent in chemistry that will do that transformation to cleave the terminal CH bond of an alkane, regardless of what the chain length is of that alkane. Okay, so we needed to figure out how to make this a catalytic reaction. And so around that time, these reagents with a boron-boron bond became commercially available. And so a metal will insert into that to make the kinds of molecules I just showed you that would cleave and functionalize CH bonds. And so with now an expensive metal, using the rhodium complexes with hexamethylbenzene attached to that, so it can slide off the metal and allow for the boron group insert into the BB bond to make the boryl ligands that would then cleave the terminal CH bonds. And so now this becomes a catalyst, and so with, I guess, what's 100 divided by 2.5, about 40 turnovers to make the product where we functionalize the primary CH bond, the terminal CH bond of the alkane. Okay? So this is the only catalytic reaction in chemistry. We discovered it, 13 years ago. It remains the only catalytic reaction in chemistry that will functionalize the terminal CH bond of an alkane with, again, with good selectivity. Okay, so, but the second aspect is to functionalize the CH bonds of these aromatic rings, these flat rings. And so we can do that with hundreds of turnovers, not 10,000 with this original catalyst, but with hundreds of turnovers. So could we take that catalyst and that reaction on an aromatic ring and turn it into something that would be valuable for synthetic chemistry to make intermediates for pharmaceutical synthesis or agrochemical synthesis? And so we, like the BP people, switched from rhodium to iridium, and we changed the ligand to this bipyridine. So the metal binds to the nitrogens of this bipyridine, and it's that ligand that changes the property of the catalyst to now be very active for the functionalization of the CH bonds of arenes. And so the key here for the synthetic value is that the reaction occurs at the position of the aromatic ring where the classic reactions of organic chemistry doesn't occur. Right? This reaction's controlled by how accessible that CH bond is due to this distribution of the groups along the side, so how sterically accessible it is. So the reaction, if I just take this one here, the reaction doesn't occur here. Right? The reaction doesn't occur there because it's got this group there. And it doesn't occur there because it's got these two groups here, and it doesn't occur there because it's got this group here. And whereas this one has only small groups next to it. Right? And so the selectivity is controlled by the sterics, and it's very, very selective for a reaction at the most sterically accessible CH bond. Okay. So for the chemists out there, right, so if you have a heterocycle, the reaction will occur alpha to the heteroatom that's in the ring, and it depends on what the heterocycle is, and we're continuing to study what that selectivity is. But it's very reliable on arenes to go for the most accessible CH bond. All right, so what that allows us to do then is to have one reaction that does the CH bond functionalization, to install that carbon-boron bond, and then use that to make a variety of products through chemistry that we've developed in my group, but many other people have developed reactions of these compounds with carbon-boron bonds. So, for example, you can run that CH activation reaction and then make all of these different products with halogens at all these different positions, including fluorine, to make a carbon-nitrogen bond in the amines, the CO bonds in ethers, and other boron derivatives. Okay? And so one thing that we've come to appreciate is the value of this strategy, where you have one very reliable CH bond functionalization reaction to put a group onto a molecule, which then can be converted into a wide variety of other groups, whether it's reaction at an aromatic system or an allylic position, or perhaps even the terminal CH bond. We'll see how much that can be developed. So this makes carbon heteroatom bonds, halogens and nitrogens, and you can do the same to make carbon-carbon bonds. And so, again, for chemists, like the analogy here is a sterically controlled Friedel-Crafts alkylation reaction. It goes after the most accessible CH bond instead of the most electron-rich position on the arene ring, and it occurs without any of the rearrangements that you would get with a secondary alkyl halide reacting. So you can do that reaction and then this sort of coupling to make these sorts of secondary alkyl arene products, and incorporation of fluoroalkyl groups as well. Right, so it's become a very versatile reaction. Okay, so that works well. How does it work? Right, what are those steps of the cycle? I've simplified that for this talk, but we've isolated this compound. This is the active catalyst, or the precursor to the active catalyst. It's got 3 metal boron bonds to iridium, and it's got the bipyridine on here. It loses an alkene to give us unsaturated intermediate, which then reacts with the CH bond to make the carbon-boron bond. That gives this species, which then gets recycled by a reaction with those compounds with the BB bond to get back to there, and then usually it goes back to the starting point over here. So this is the rate determining step. This is the slowest step. And so if we want to make a more reactive catalyst, we need to affect that step. Okay, so I won't go into all the experiments that we've done to try to learn what controls that step, but the bottom line is that the more electron-rich that iridium is, the faster that reaction will be, is our prediction from our experimental data. And so how do we make that iridium center more electron-rich? Okay. So these are the reactive ligands, right? So we're not really going to change those. So the only thing we can really do is change that bipyridine to something else that would be more donating. Okay, so how do you tell how much electron density is on the metal center from one compound versus another? Well, usually you put a carbon monoxide bound to that, and then you measure the CO stretching frequency. That depends on how much electron density is at the metal. The lower the number, the more electron-rich the metal is. And so we went through some of the classic ligands that you might imagine replacing bipyridine with on the iridium to make a more electron-rich metal center. And I would have thought that trimethylphosphine would be particularly electron donating, but it turns out that's not the case. Bipyridine is more donating, dimethylbipyridine is more donating than that. And so our guess was that tetramethylphenanthroline, I'll show you the structure in a minute, is going to be even more electron donating. All right. So here's our diethyl-butyl bipyridine. And so if we want to do that same reaction with the iridium catalyst as we did with rhodium, functionalize a primary CH bond, the reaction doesn't occur. Okay, very little product with diethyl-butyl bipyridine. So it's a great catalyst for functionalizing arenes, but it's a terrible catalyst for functionalizing alkyl CH bonds. But if we change the ligand to this one, this tetramethylphenanthroline, now we get 80% yield of product out, functionalizing the primary CH bond under lower temperatures than we did with the rhodium system. Okay, so that reactivity still doesn't constitute a synthetic method because people don't care that much about this particular reaction. It's a very much of a model reaction, and it has to have neat solvent. But the point I want to make here really is that this is why it's so hard to design a catalyst. Right, look at this. So you've got no reaction with this ligand on there attached to the metal. And if you look at the difference in structure here, we just strapped that together, and we took this alkyl group off and changed to 2 alkyl groups there. Pretty small change, but it goes from 0 to 80% yield. You can't pull out a piece of paper and you can't get a supercomputer to calculate that. Right? Knowing that information now, right, we can maybe go back and figure it out. And the person sitting 3 rows down from the back in the middle is trying to figure that out. So Shen Li, who's actually one of the Einstein people working in my lab, is trying to do some calculations to figure out, what can we rationalize this difference in activity. But you couldn't start from nothing and then calculate the catalytic cycle and all the different pathways and then say, okay, that's going to be the ligand you should make and do that. Okay. So that's why it's so hard. But once we know that, right, that makes a more active catalyst, we can do new things and functionalize CH bonds in new ways. And so one thing Matt thought about is using silicon instead of boron, right? So that boron and silicon compounds have similar, but not the same, but similar reactivity. And so the scheme was to take a carbon-oxygen double bond, attach silicon to the top of that, to the oxygen here by doing a hydrosylation. And now this is an intramolecular reaction. Instead of the 2 molecules having to come together, now you can wrap around and functionalize the CH bond with silicon. So that was a pretty good reaction. It actually has a silicon-oxygen bond on it, so we can functionalize it afterwards, right? But another strategy, right, was to try to do this on an alkyl CH bond, where you would start with an alcohol or a ketone or carbon-oxygen double bond, hydrosylate, or somehow attach the silicon to the oxygen. But now wrap around and grab onto a primary CH bond, like the strongest CH bond in the molecule. And to get this product, and if you get that, then it's known that you can do this Timau-Fleming oxidation to install a carbon-oxygen bond in the product. So you'd start with these very common materials and then reach around and functionalize the primary CH bond in that molecule. So this strategy works. This was our initial paper here. The strategy works. And this sort of, long story short, the marquee reaction is this sequence. So we take this molecule, which has a double bond and an ester in it, and it has many different CH bonds. And we can use the iridium and the silane and put silicon on the oxygen. That's not too hard. And now it reaches around and it'll grab one of those, the hydrogen on one of those two methyl groups. Now this gets back to this right-hand, left-hand business, right? So this is a chiral molecule, and that's, let's say, left-handed, right, that position of the molecule. And this would be the left-handed methyl group and the right-handed methyl group, right? And so those two methyl groups are different. And can we selectively do the reaction at one methyl group over the other one? And it turns out we can. So we can do that sequence and install a carbon-oxygen bond, and it only occurs at that methyl group that's off the back. We don't really understand why, but it is completely selective for that methyl group off the back to make the right, one combination of the two-handedness of that. Okay, so chemists have done this before. Synthetic chemists have done this before. This was done in this paper and not too long ago. But it took 10 steps to go from here to here. And this is, I've drawn it as 2 steps, but it's really just in one pot. You add this, and then you add that, and then you add that, and you go from here down to here very selectively. Right, so it's a different way to do synthetic chemistry where you're doing the reaction at a carbon-hydrogen bond instead of at another functional group. And so maybe my favorite example of all of that is this one that I'll example of the CH activation is to do a reaction on these 3-membered rings, cyclopropanes. That CH bond's a little more reactive than the CH bond on these long chains. But still, right, we can take that chemistry and we can do a reaction at the carbon-hydrogen bond of a cyclopropane. And again, back to the 2 hands, right? So that's a stereocenter, that's a stereocenter. You got the left and the right hand, you get a single, or mostly one diastereomer out in many of these cases. But you've got a functional group here, 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 and the reaction does not occur at any of those functional groups. The reaction occurs at the carbon-hydrogen bond. Right? And so it's completely complementary to the type of chemistry, again, that one would learn in introductory organic chemistry class. And so we can take, again, this one reaction to get to here. We can't do as much with this, but we're starting to develop that. And you can go to other boron derivatives, but you can also go to amines, alcohols, and do cross-coupling to make new carbon-carbon bonds. Right? Again, from one transformation, you get can make a family of products. All right, so that's a short story on the Bohr relation. Let me just finish by spending just a couple minutes, maybe 3 to 5 minutes, on this question of whether there's a more systematic way to discover such reactions, right? So I mentioned that the observation of the CH activation was a serendipitous discovery in my group, just like olefin metathesis and olefin polymerization were serendipitous discoveries. Right? So is there a way to do this in a more systematic way? And so this leads to this concept of so-called high-throughput reaction discovery or high-throughput experimentation, which is a pretty, a type of approach to doing experiments, which is sort of being taken up by a lot of different groups in industry as well as in academics. But what we introduce is this concept of doing this in a multi-dimensional way. Okay, so if I'm in the Merck process group, I'm in a process group at a pharmaceutical company, and I got to make this molecule because it's going to lower blood pressure. Okay, and I got to figure out how to make that carbon-carbon bond, and I got to get the right catalyst, the right solvent, the right base, the right temperature. And so I can take a library of catalysts off the shelf. I can get a lot of different ligands. I can test those at different temperatures, different additives, and I can figure out how to get one to react with two and to make that bond. Okay, so that's one challenge. The second, though, is one that we started to look at, is whether we could discover new reactions by not just having 2 substrates together, but having a whole family of these together, or like a party full of these different substrates all in the same flask in the same room. And then you bring in this matchmaker. Remember the chemistry.com matchmaker thing, right? You take that matchmaker in there, and you figure out which molecules are going to go together, match up the different molecules. And then you have to figure out which ones are matched up with which ones. And so if you've got this whole collection of different molecules in there and you've made bonds between some of them, how can you figure out which ones you made bonds between? Well, you measure the masses of them. Okay? And so the design here, there's many design elements. Well, one of the main ones is very simple. We have these substrates, and down in this group, all approximately the same molecular weight. Not exactly the same molecular weight, but approximately the same molecular weight. And so if a bond formed between those two, you get about double the molecular weight. And you just use mass spectroscopy to figure out which ones formed a bond. Okay. So here's the, skip this, here's the, oh, that's right. So here's the different substrates. There are a huge number of possible substrates in there, but we've got some of these that have the carbon-halogen bonds, some with OH bonds, some that are alkanes that would be on reactive alkenes, alkynes. And so we're going to try to figure out which functional groups are going to react with which functional groups in the presence of catalysts. Okay, so the setup then is this. So along this axis, we use different metals. And I'll get back to that in a second. Along this axis, we're going to use different organic groups, the ligands that you attach to the metal. And then in each one of these wells of a 96-well plate, 8 this direction, 12 that direction, there are 17 substrates, arbitrarily chosen number. Actually, we chose the number so that in the end, the experiment would be would have 50,000 possible reactions. Okay, so the second thing, what we do for our analysis is instead of doing 96 mass specs, we actually only do 20. So we take the rows and we pull them all together. And so we do 8 mass specs of the combinations here, and we do 12 along this axis. And then if we have the same molecule, same mass spec here and here, then we know that catalyst is the one that formed the bond between them. So we don't actually have to do 96. It's not that big a deal to do 96, but if you think of starting to really ramp this up into a real, high throughput workflow, then that 5-fold difference is a big time savings. All right, and so as I said, if you take the metals, the ligands, the substrates, you get up to 50,000 possible reactions that we can assay in a day. Okay, so the kinds of catalysts that we looked at then was to emphasize the metals that were not in the circles on that periodic table I had before. So to look at the metals that are outside of the typical metals, the rhodiums and the iridiums and so forth that are used for catalysts. So we have in here some copper and nickel and cobalt and terbium and tungsten and so forth. And then different organic groups that are we thought likely would bind to those sorts of metals. So this is something we're continuing to do in my lab, but I thought I would just give you one example of how this works. Right? So we identified a, quote, new reaction because we have a molecular weight. We have a peak here that has a molecular weight of 315. And so that molecular weight is the combination of this alkyne plus that amine, and the NH bond adds across the triple bond to give this product called an imine. We can reduce that to isolate it. Okay, it's actually a known reaction, but it's known to be catalyzed by gold, rhodium, and palladium, the ones within the circle. But we can catalyze that with just copper. Right? Dirt cheap, one of the least expensive metal complexes will catalyze that transformation. And if it did that within all of these, with all these other functional groups around, it should tolerate those functional groups when it does the reaction. In fact, you can have all these other groups and the yields are pretty solid. Okay, so that's a new way that one can think about trying to discover reactions. And so the question then is, is that some great lead that would lead to a 20-year research project, or is that just sort of one paper, right? So that particular reaction is not the most important reaction. But there are some other ones that we're looking at of additions to alkenes and alkynes that have inspired us to develop new additions of aromatic CH bonds across alkenes with different selectivities. That is very preliminary, so I didn't present it here, but we hope will turn into an important new reaction. All right, so just to wrap up then, right? So the goals for research in chemical synthesis, and most generally stated, are to create new molecules with new functions. Right, like pharmaceuticals, agrochemical, light-emitting diode components, and so forth, or to make known molecules by more efficient methods or energetically more efficient with renewable feedstocks. And what's clear is that catalysis is the way to do that, right? So almost every new reaction, if you open a chemical journal, almost every new reaction that's developed is a catalytic reaction. Some of them with metals, some with the transition metals, some with main group metals, some with organic compounds, some with enzymes with metals in the middle, some with enzymes with organometallics, the kinds of iridium, rhodium types of things in the middle of those. And many people in the community are working to develop those sorts of catalysts. Right? And a large fraction of them are then with heterogeneous catalysts that are perhaps the most practical for large-scale synthesis, and then some of them are sizes in the middle, so the nano-scale catalysts that are not bulk metal but are not molecular catalysts. So there's a whole group, different array of groups that are working in different areas trying to do the kinds of reactions that I talked about here. All right, so I'll end there and just say that people who've worked on the CH activation chemistry in my lab are listed along here, from the people who did the very first observations to Carl Liske and Eric Simmons, who's been using the latest catalyst, and Shen Li, who's been trying to figure out through computational methods how that works and has developed some new methodology with that as well. Actually, I neglected to mention that, I always do that, first time, that the iridium catalyst was developed with Tatsuo Ishiyama, who was a visiting scientist in my group. But is actually in Hokkaido, is now an associate professor in Norio Miyaura's group of the Suzuki-Miyaura reaction, which was the subject of the Nobel Prize with Negishi. So he's been in the mix of developing reactions with boron reagents for many years. And then the reaction discovery people are here, and it was actually Dan Robbins who was the one who really made the practical system built off of Seth and Carl's early designs that turned out to be too complicated, but were elegant but too complicated and have never seen the light of day in the published literature, but Dan's figured out how to do it in the way I showed you. So thanks to all of you for coming. I really appreciate your attendance, being part of the Einstein program, Matthias for his invitation to participate in this, and I'll take any questions if you have time.
I still wonder about this catalyst that activates the strongest CH bond in a molecule. I didn't get any explanation for that. Can you
why that selectivity?
Yeah.
Well, I guess it's really the same reason as you get selectivity for the most sterically accessible CH bond on an arene. Right? It's a steric effect is the simple answer. Right? So that CH bond is the most accessible to the catalyst. The real answer is more complicated, and that is that at least the rhodium catalyst, the first catalyst, will actually cleave both primary and secondary CH bonds. It has a 7-to-1 ratio of rates for cleaving the primary and secondary CH bonds, but the overall selectivity is like 1,000 or 10,000 to 1. So it's not just the rate at which the CH bond is cleaved. Then that's reversible, and then the real selectivity comes from making the boron carbon bond. Now the boron group is reasonably large, and so it's hard to get that group next to a secondary carbon. But so the reductive elimination step, or the coupling to make the BC bond, is a much higher barrier with a secondary position than with a primary position, which is probably the origin of the hydroboration selectivity as well, right? So that's the origin of that. For the iridium catalyst, we think that the CH bond is cleaved irreversibly, and maybe that's why the selectivity is a little bit lower. For the linear alkane, we only saw the terminal product, but we can functionalize secondary CH bonds with that catalyst, and we can't with the rhodium one. And maybe that's because it's an irreversible cleavage of the bond. That's the highest barrier, and the coupling step is faster than it is with the rhodium system.
Very interesting also this high throughput screening. How much can you accelerate your discovery of new reactions, and how many PhD students get unemployed by this?
How many what? How many employed?
PhD students get unemployed and cannot finish a thesis because you just do it by a machine.
Well, okay, so it remains to be seen how many reactions we can discover. I mean, so we have a hydroaerylation with aryl halides, we have a hydroaerylation with boronic acids that let us to at least think more about the problem in general, and some other catalysts for nickel catalysts for hydroaerylation. We have this hydroamination. The hydroaerylation of alkenes, which was sort of a tangent of the discovery process, but could be a very important reaction depending on how well we can develop that. But there are, if you looked at the data, right, there's a lot of peaks in the mass spectrum for a lot of things that are coming together to make a reaction. Now, if we analyze all those, maybe we'll discover that, or trigger us to think about a reaction that we wouldn't have thought about. So some people argue that we'll never get anywhere with this because there's no hypothesis, right? It's just a completely random look for things. Not completely random because we put the molecules in there, but it's a pretty random look. So I guess where I'm optimistic about being able to discover new reactions is when you think about a new ligand, right? So if you got, we in the area, right, we think about, well, if you had this group here and this group there, that would be a ligand, family of ligands that one could make lots of combinations of. So how do you tell what the chemistry is going to be for that ligand? Right, a lot of people will make a ligand and then they'll do an allylic substitution reaction and maybe asymmetric hydrogenation or something, a known reaction. So how do you figure out what that ligand would do that might be some new reaction that other catalysts don't do? So I think this would be a way to figure that out. right? So there would be the design of the ligand rather than just taking these sorts of things that we tried, right? That, very hindered or more electron rich, electron poor, or push-pull, or whatever they are. And then combine those, figure out how you make the complexes, and combine those in a reasonable way, and then put them together and see what they do. So the thought, though, is that you would then discover, I don't know, let's say you discover 5 new reactions, right? That would be potentially very interesting. So now you have to figure out how to improve them and turn them into something. And the hope is that you could do better than we've done with the borylation, where it took us 18 years to get from the initial discovery to something that, where we could go back and get a functionalization of an alkane in a practical way. So nobody's going to be unemployed. You create, I don't think, I'm not going to, right? But you would create a lot of new reactions that people could, in my group or other groups, could work on. So that's the hope. We'll see if it plays out that way or whether it's just a little cute thing that disappears. But we've been trying to work on new ways to do catalyst discovery as a side project for many people over a decade or so, or 15 years. So I think this is more promise than the other ones that we did.
I think one of the advantages of this approach is also we also have to learn the tolerance of catalysts for doing the specific reactions. So instead of, I would say it's maybe not in first focus to find new reactions, because then the problem starts with the scaling. Once you go from milligrams to kilograms, the mechanism don't work. So I think a big issue could be also the tolerance of catalysts. So you could have
right. Well, there's 2 issues with this, right? So the approach here, where you've got all these functional groups together, the reactions have to tolerate the other functional groups, right? Now, one molecule, one of the components might change the catalyst to make it active for something else, right? And one of the design elements, I think it was in those bullet points, we actually add excess of the metal. So if a nitrile would poison the catalyst, there's extra metal in there, so it wouldn't poison all of it. But still, you would never discover a Ziegler catalyst with this because there's too many functional groups in there, right? So, but the thought is that if you discover a reaction through this process, that instantly that would be a reaction that would be very tolerant of other functional groups and would be the kind of reaction that a synthetic organic chemist might want to use. So maybe it's not a way to discover new commodity chemical reactions for the next tighter formulation or something like that, because in commodity chemicals you don't care about functional group tolerance as much.
So I'm not a chemist, and I'm happy I do something simple like mathematics and see how complicated all this is. But so I have a very simple question. What is it that makes a chemical compound a catalyst for some reaction? Is there some simple explanation? Is it, say, energy interaction, conformation dynamics, geometry, all of that, or what is it? What is it? Just some simple principles that you can say that bring things into catalysis.
Yeah, so in terms of, if you just think about the energy landscape of the reaction, it can never go too far downhill, right? So if you have lithium aluminum hydride that you're going to use to do a reduction, it's very reactive. It burns in air, and if that reacts with a carbon-oxygen double bond, it makes an aluminum-oxygen bond that's really strong. And so you start from here, way up here at these high-energy reagents, and you fall way down here. So it makes it a very reliable reaction, and it's very exothermic, but you can't get back out of there because your catalyst has to go back to what it started from, and so it goes all the way down here. It can't get back up to there because it's fallen too far in energy. So the thought is that each one of these steps has to have low barriers, and it also can't go too far down. So you've got the catalytic reaction never changes the thermodynamics of the overall reaction because it doesn't change, right? And so if you start here and your products are here, and then there's a reaction the catalyst does that gets you down here, you got to get back out of there and back up, right? You need too much energy to get back up. So no reaction can be too far downhill is part of what it is. And it just turns out that transition metals have weaker bonds than organic compounds as a general rule. So the formation and cleavage of those bonds never costs as much energy as it does when you do something with a main group in an organic compound. So I guess that would be a general principle. And you always have to figure out a way to get back to where you started from. So you can add a borane to a double bond, And we did all this CH activation to make boranes, but it can't be catalytic in boron, because to cleave the boron carbon bond, you got to do something more aggressive. And so